Few topics. Hello students, let me revise few topics on interference. The theory of interference, expressions, derivation, all those things can be found in the previous video. Please check in the second PUC physics channel. Interference is the redistribution in the intensity due to superposition of two or more waves of same frequency and same nature. So, what is the condition for constructive interference? Constructive interference in terms of phase difference. Constructive interference in terms of phase difference, phi equal to 2n pi, where n equal to 0, 1, 2, 3, etc. Substitute 0 here, we get 0, n0 in this, we get 0, n1 we get 2 pi, 4 pi, n2 4 pi, n3 6 pi, etc. In terms of path difference, denoted by delta, path difference by delta equal to n lambda. Again substitute 0 here, 0, substitute 1 lambda, substitute 2, 2 lambda, 3 lambda, etc. So for constructive interference, phase difference between the waves must be even integral multiple of pi. For constructive interference, path difference between the waves must be integral multiple of the wavelength of waves. Similarly, for destructive interference, phase difference between the waves should be 2n plus 1 into pi, where n equal to 0, 1, 2, 3, etc. Substitute 0 here, we get pi, substitute 1, 3 pi, substitute 2, 2 into 2, 4 plus 1, 5 pi, and in terms of path difference, delta stands for path difference, 2n plus 1 into, in place of pi, lambda by 2. Substitute 0, 0, we get lambda by 2, half of the wavelength. Substitute 1, 2 into 1, 2 plus 1, 3 by 2. So it is 3 lambda by 2, 5 lambda by 2, 7 lambda by 2. So odd integral multiple of half of the wavelength. So condition for destructive interference in terms of phase difference is odd integral multiple of pi. Path difference between the waves must be half odd integral multiple of the wavelength. So phase difference means it should be in pi. Path difference means it should be in lambda. Lambda, path difference, meter in terms of length, meter. Phase difference in terms of radian. Okay. For constructive interference, phase difference is to n pi, that is 0, 2 pi, 4 pi. Now let us understand phase difference between two waves equal to 0 using waves. Let this be a wave, first wave. Okay. This is x-axis, y-axis. Amplitude of this wave is A. Phase of this point is 0, because if this is a wave, this is 0, pi by 2, pi, 3 pi by 2, and this point is 2 pi. See, this point is this point, therefore phase is 0. I am talking about phase difference equal to 0. Let me draw second wave. This is second wave. Okay. Amplitude of second wave is B. This second wave also starts from the origin, from this point. Phase of this is 0. Phase of first wave is 0, phase of second wave is 0, thereby difference is also equal to 0. Difference of these two, 0 minus 0 is 0. So if these two waves interfere, what we get is constructive interference. Their amplitude is maximum. So let us find amplitude. Students, you know expression for amplitude, root of a square plus b square plus 2ab cos phi, where a is amplitude of first wave, b is amplitude of second wave, phi is phase difference. In this case, phase difference is 0, equal to root of cos 0 is 1. Therefore, it is a square plus b square plus 2ab. So this is nothing but a plus b whole square under root gives a plus b. Okay. This is amplitude of the resultant wave. If these two waves superpose, what we get is the resultant whose amplitude is a plus b. This is a, let this be 1 centimeter and this is 1.5 centimeter. If these two superpose, what we get is 2.5 centimeter wave, bigger wave, such bigger wave. So amplitude of this is a plus b. That is the meaning of constructive interference. Now another way of visualizing constructive interference. This is crest point. This is crest. Crest on crest. Trough on trough. Crest on crest. Let me write. Crest on crest. Trough on trough. If crest of one wave falls on the crest of the other, trough of one falls on the trough of the other, that results in constructive interference. In constructive interference, amplitude is a plus b. This is maximum, and also intensity is also maximum. Intensity is also maximum. Okay. This is how you should visualize constructive interference. Now, destructive interference. In the case of destructive interference, phase difference should be equal to 2n plus 1 into pi, isn't it? Or you can also write this as pi, 3 pi, 5 pi, 7 pi, etc. Now let us talk about phase difference equal to pi or 3 pi. Simplest case, pi. Understand the waves. This is first wave. Amplitude of first wave is A. Okay, this is A. This point is 0. This point is pi. After mean position, the graph should go towards the negative side. Okay. Now, let me draw second case. So, after this mean position, if this is x-axis, after the mean position, the graph is going down. Means this point is similar to this point, isn't it? So, phase of this point is pi. Phase of this point is 0. Difference of these two is pi. Difference of these two is pi. So if these two waves interfere, what we get is the destructive interference, the pattern of destructive interference. Now, if A is 1 centimeter, this amplitude is B, which is equal to 0.5 centimeter, as an example. Then amplitude equal to root of A square plus B square plus 2AB into cos pi, because I am talking about pi. Cos pi is minus 1. If this is minus, this becomes minus. If this is minus, then the resultant is A square plus B square minus 2AB equal to A minus B, isn't it? So amplitude of the resultant equal to A minus B, and this is minimum amplitude. A minus B whole square under root means it is A minus B. Now, A is 1 centimeter, B is 0.5, 1 minus 0.5 is 0.5. When these two waves superpose, what we get is the resultant, and resultant 1 minus 0.5 is 0.5. Resultant should have 0.5 centimeter, like this. So this is A minus B equal to 0.5. Now, how to visualize this? This is crest. This is trough. Crest on trough. Crest on trough. Trough on crest. Trough on crest. Crest on trough or trough on crest results in destructive interference. Crest on crest, trough on trough results in constructive interference. These two are important points to understand the next topic. Please do remember. Now, Young's experiment. Before going to Young's experiment, let us understand interference in the case of water waves. If I am tapping the surface of water at regular intervals like this, then that produces ripples. So these are the ripples. Such patterns you might have seen on the surface of water, isn't it? This is the point of disturbance. Point of disturbance is similar to source. Source of disturbance. If I keep tapping, then ripples are produced. What are these lines? These lines are wave fronts, locus of points which are in phase. These are crest points. Crest points. If I draw dotted line, then in between two crests there should be a trough. So this is trough. Crest, trough, crest, trough, crest. So this is how ripples are observed from top view. Top view. Now how about side view? If this is the point of disturbance, then a wave travels like this. Crest, trough, crest, trough, crest. For time being, neglect the decrease in amplitude, because as we go from the center, away from the center, height of the wave decreases. Nothing but amplitude of the wave decreases. Neglect the decrease in amplitude. Assume that amplitude is almost same. So crest, trough, crest, trough, crest, trough. If this is the wave pattern, crest, they are represented by straight line, trough dotted line, crest straight line, trough dotted line. Okay, crest smooth line, trough with dotted line, dash. If this is a cardboard with two slits, there is a small gap. At these 2 points, if this is the surface of water, okay, if this is the surface of water, if I tap the surface of water at these 2 points like this, if I keep tapping the surface of water at regular intervals like this, then ripples are produced. So they look like this: ripple, crest points. This is the crest points. Similarly, from this, the crest points. After crest, there should be trough. Trough is represented by dotted line, trough. After that, I should represent crest, crest, trough, crest. Then like this. Then dotted line, trough points. Here also trough points. Students, I hope you understood at least little bit. If I continue to draw crest waves and trough waves, crest waves, trough waves, then the pattern looks like this. Here lies two gaps, A and B. So we are tapping the surface of water at A and B. Here green lines represent crest points, locus of crest points. These are wavefronts. Red represents trough points. Identify center of these two, A and B. That is this point. Okay. See, green crest points. At this point they overlap. So crest on crest means that leads to constructive interference. Move a little bit away. See, green of B, waves from B, and waves from A, crest of A, crest from A. Again crest on crest. So these two interfere constructively. Can you observe red on red, trough on trough, constructive interference, crest on crest, constructive interference, trough on trough, constructive interference, constructive interference. So constructive interference means this results in bright band. Let me write bright fringe. Fringe means band. Now here red line is overlapping on green line. So this is crest on trough, trough on crest, crest on trough. Can you observe these regions? So if I join all this, then this results in destructive interference. Here constructive interference, this results in destructive interference. Destructive interference means intensity should be less, minimum. So in this case, this is the region of dark fringe. Dark fringe means destructive interference where intensity is minimum. Okay. Bright fringe means intensity is maximum. Next, let me move sideways. Again we can say crest on crest, trough on trough, crest on crest, trough on trough, crest on crest. This results in constructive interference. So constructive interference, destructive interference, constructive interference. Again here crest on trough, trough on crest. Students, please take time to understand. Red color means trough, green means crest. Trough on crest, crest on trough, trough on crest. This results in destructive interference. Destructive. See, constructive, destructive, constructive, destructive. Similarly, on the other side, crest on trough, trough on crest on trough, trough on crest, crest on trough. So this results in destructive interference. D for destructive. Similarly, here these points, crest on crest, trough on trough, constructive interference. Constructive, destructive, constructive, destructive. So on the other side also same thing, constructive, destructive, constructive, destructive. So using waves, one can explain alternate constructive and destructive regions. Constructive bright fringe, destructive dark fringe. Now let us see what do you mean by bright fringe and what do you mean by dark fringe. Now in the case of light waves, this is the first cardboard with a narrow slit. So small portion is cut and opened. Now let us keep second cardboard. In the second cardboard, let us keep two narrow vertical slits like this. And the third cardboard is the screen, some white background. Okay. If there is a source of light, this is source, monochromatic source, monochrome means single wavelength, only one wavelength. Then light from the source travels in all directions. But since there is a cardboard with narrow slit, in this small region light emerges. So this light falls on the second cardboard with two slits, and only that portion of light which can pass through these two slits can escape. And on the screen, surprisingly, what we see is alternate bright and dark bands like this. Students, understand? Let me explain. Single slit. Let me cover one of the slits. If this is single slit, this is also single slit. What we find is uniform intensity, uniform illumination, just like this portion of the paper. This portion of the paper is equally illuminated, uniformly illuminated, isn't it? Same thing is observed on this screen. Forget these bands, uniform illumination. Now, this slit is open, second slit is closed. Light from the source passes through the slit. Second cardboard, single slit. Again on the screen we find uniform illumination, just like this. No pattern, nothing, just uniform light. But when these two are open, strange thing happens. Instead of increased brightness, Thomas Young observed alternate bright and dark fringes, bands, fringes, bands. So these bands are called fringes. Okay, bright band, dark band, bright, dark. Bright bands are the regions of constructive interference. Dark bands are the regions of destructive interference. So upon careful observation and careful experimental setup, he could get this pattern. So this is that experiment which supported wave theory of light, wave nature of light. Students, observe this. Cardboard supported by a stand, monochromatic light. When light passes through a slit linear source. Can you recall wavefronts due to linear source? Wavefronts due to linear source is cylindrical. So these are cylindrical wavefronts. Cylinder observed from above looks like a circle. So that's why it looks like circular wavefront, but actually these are cylindrical wavefronts. See, cylindrical wavefronts. Second cardboard with two slits S1 and S2 separated by small distance d. This light emerges through these two slits. See, and when they overlap, crest on crest, trough on trough, or crest on trough, trough on crest, depending on the condition, alternate bright and dark bands are observed on the screen. This is the screen where bands are observed. So this is that experimental setup. In the previous setup, I showed the slits horizontally, vertically, but here horizontally so that I can show the bands properly. Okay. So this is double slit experiment. On the screen, there is interference pattern, means pattern similar to this. Pattern similar to this. If this is center of the screen, then there is a bright fringe. So this is called central bright. So after central bright, there is a dark fringe. This is first dark. After dark, there is bright. See, central bright, dark, bright, dark, bright, dark. Central bright. On the other side also, dark, bright, dark, bright. So there is alternate bright and dark fringes on either side. So this is called the interference pattern, and these are called the fringes, bands, interference bands. Distance between two slits and the screen is capital D. Distance between the slits is small d. Wavelength of light is lambda. So we have to derive an expression for fringe width denoted by beta. Fringe width denoted by beta equal to lambda capital D by small d. Students, every time please tell capital D by small d. Capital D is distance between slits and the screen. Small d is distance between the slits. So lambda capital D by small d. Lambda capital D by small d. Okay. So what is fringe width means? Width of bright. So this is width of bright. And then dark. So this width is fringe width, beta. Or else distance between adjacent dark fringes. Distance between adjacent bright fringes. If you carefully observe, this is this and this is the bright fringe. Next bright fringe is this. So this width is beta. Distance between adjacent bright fringes, or this is dark fringe, dark. This is next dark. So this is beta. Distance between adjacent bright fringes or distance between adjacent dark fringes is the fringe width. We have to derive an expression for fringe width in terms of lambda capital D and small d. Okay. Expression for fringe width. This is for 3 marks, 4 or 5 mark question. Okay. Derive an expression for fringe width in Young's double slit experiment. This is one of the methods to derive the expression. A and B are two slits separated by distance D. And this is the screen. This is the median. From A and B, light emerges, and let this be some point P on the screen. So P is a point at a distance x from center of the screen. Okay. So this P receives light from A and B. Students, remember, each and every point on the screen receives light. So this is one such point. Since we are interested in this region, we have to show light reaching that point P. So this is the first ray from A to P. This is second ray. These are by construction. Let me draw a dotted line just in front of A. Similarly, from B. If distance between A and B is small d, then this distance is d by 2. This is another d by 2. Center of the screen, O. Distance of P from center of the screen is x. So this distance is x. Students, draw this diagram neatly using scale pencil. You don't have to draw this using colored pen or sketch pens. And in examination, don't forget to draw direction of light, arrow marks. A, B, P, center of the screen O. Let this point be E and this point is F. Distance between A and B is small d. Distance between slits and the screen. So this distance is capital D. Now let us write few statements. Let A and B be two narrow slits separated by small distance d. Let d be the distance of the screen from the slits. P is a point. Let P be a point on the screen at a distance x from center of the screen. Center of the screen O. Students, copy the diagram and these statements and let us continue with the derivation. Consider big right angle triangle BPF. in triangle BPF, let me use Pythagoras theorem. BP square equal to BF square plus PF square. BF square plus PF square. PF square. BF is nothing but capital D. D square plus PF. P to O is X. O to F is D by 2. So it is X plus D by 2 whole square. Students, refer diagram and then try to write the equation. BP square. Now, in small right angle triangle, in triangle APE, APE. Again, Pythagoras theorem, AP square equal to AE square plus PE square. AE square is nothing but D square plus PE, X minus D by 2, isn't it? So it is X minus D by 2 whole square. This is AP square. BP is longer than AP. See, BP is longer than AP. So that's why BP square minus AP square. Let me consider BP square minus AP square. BP square is D square plus X plus D by 2 whole square minus square bracket D square plus, this is minus, isn't it? X minus D by 2. Good. X minus D by 2 whole square equal to D square get cancels. Let me expand this. It is of the form A plus B whole square, X square plus D square by 4 plus 2x D by 2 minus X square. This is of the form A minus B whole square plus D square by 4 minus 2x D by 2. Left hand side is of the form A square minus B square. Therefore, BP minus AP into BP plus AP. X square get cancels. Minus D square by 4 plus D square by 4. This get cancels with this. 2 get cancels. XD minus minus plus, again these two get cancels. XT. XT plus XT is 2XD. BP plus AP. Let me bring this to denominator. Left hand side is BP minus AP. Now, what is BP minus AP? Look at this diagram. BP is path of light. AP is another path. So BP minus AP is path difference. Isn't it? Simple concept. Don't break your head. BP is one path, AP is another path. Difference of those two is path difference. Here BP minus AP equal to delta is the path difference. Therefore part difference delta equal to 2xd by bp plus ap. So this is the expression for part difference. Delta equal to 2xt by bp plus ap. Now in the actual case, small d, this small d is very small. Small d is in terms of millimeter, and capital D, distance of the screen from the slits, is in terms of meter. D is in terms of meter. So meter is 1000 times the millimeter. So this is very large compared to distance between the slits. So let me use the condition. If small d is very much smaller than capital D, then interference fringes can be seen only in this small region. Okay. That time this P should be well within this point. Students, please don't disturb the diagram. Just to explain, I'm using all these things. P should be well within this point. If here lies P, then from A to P is almost equal to B to P. So I can write AP is approximately equal to BP, approximately equal to capital D. So let me use this condition. Okay. What's the condition? If small d is very much smaller than capital D and P is very close to O, then AP is almost equal to BP equal to D. Okay. If D is very much smaller than capital D and P is close to O, then AP almost equal to BP equal to D. This implies that delta part difference equal to 2xd by BP is D. AP is also D. 2xd by D plus D is 2D. 2 get cancels. Therefore part difference equal to xd by capital D. So we have the expression for part difference in terms of xd by D. Students, understand? Two slits, screen, there is interference pattern. Now let this be the slits, screen, and P is far away, because if this is very close, we can't draw all the things clearly. So let us make it big. Okay, blob diagram. Now in this case, if fringes are like this, alternate bright and dark fringes, and at P if there is a bright fringe. Bright fringe means constructive interference. For constructive interference, what is the condition in terms of part difference? Part difference should be equal to n lambda, isn't it? So let us use this condition for constructive interference. Let me repeat. If a bright fringe is formed at P, then part difference between these two waves must be integral multiple of the wavelength. If a bright fringe formed at P, if bright fringe is formed at P, then part difference for bright fringes is n lambda, where n equal to 0, 1, 2, 3, etc. Implies that n lambda equal to xd by capital D, or x equal to n lambda capital D, n lambda capital D by small d. This is central bright, C B, central bright, first bright, second bright, third bright, fourth bright, fifth bright, sixth bright. Let the sixth bright be nth bright, nth bright. Then fifth will be n minus 1, isn't it? So instead of mentioning that with a number, let me denote it by n. This is nth bright, previous is n minus 1th bright. And here x stands for distance of nth bright fringe from the central, from the center of the screen, nth bright fringe. That is the distance of nth bright fringe. Let me denote the distance by xn. Instead of x, xn. N lambda capital D by small d. Now for n minus 1, n minus 1th bright fringe, for n minus 1th bright fringe, x n minus 1. This is just a notation. In place of n, write n minus 1. So previous, lambda capital D by small d. Now let me take xn minus xn minus 1 equal to xn is n lambda capital D by small d minus xn minus 1 is n minus 1 lambda capital D by small d equal to, in these two, lambda capital D by small d is the common factor. Remaining is n minus n minus minus plus 1. This is xn minus xn minus 1. These two get cancels. What we left is lambda capital D by small d. Students, what is xn minus xn minus 1? Students, this is n, the previous is n minus 1. Distance between n and n minus 1 means distance between adjacent bright fringes. Distance between adjacent bright fringes is nothing but fringe width. Distance between adjacent bright fringes called the fringe width, beta. Similarly, we can show that distance between adjacent dark fringes is also lambda d by d. Let us not show those steps. Let us just write. Beta equal to lambda capital D by small d. Therefore, fringe width is lambda capital D by small d. So fringe width is directly proportional to wavelength. Fringe width is directly proportional to capital D, that is distance between slits and the screen. And fringe width is inversely proportional to small d, distance between the slits. Students, copy the derivation. Looking at the derivation, write twice, and without looking at the derivation, write thrice, without looking at the notes. Okay. So in one stretch, write 2 times or 3 times and practice. This is an important derivation in interference.